Here we're going to take a look at a dental polymer, which is an example of a radical polymerization. For reference, if you are interested, it is found in the Journal of Chemical Education, and their pictures are a lot cooler than the demonstration you're going to see here also. So first off, radical polymerization. If you're kind of new to radicals or you need a review, please see the video description. There's a link there that'll give you kind of a rough walk down on what are radicals and how they would go through and function. As a quick review, what we're looking at within this is we would start with some kind of radical initiation. That initiation is usually started through some kind of peroxide bond, and that bond being with two electronegative elements really wants to split apart. So we can hit that with a little bit of light. Light comes in, and what that will do is initiate the radical formation, and we'll split this into two radicals. Those two radicals could then go on to start the polymerization reaction. Okay, or if it was a radical reaction, they would go through and initiate the radicals for our subsequent reactions. So as we continue, or what we might reference this as, is that this would be the initiation step. In the initiation, we don't need a lot, we just need something to get this started. Because of the polymerization itself, it's going to self kind of feed and self-fulfill. So we don't need a whole lot of this initiator, but we do need some of it present. Once the initiation has happened, we now have to get that initiated molecule or the initiator to now react with our monomer. And so what we're looking at here is a basic simple alkene is a better word for this. And our alkene is reactive because of that pi bond. So what the radical can do is we can take that single electron and we can cause that pi bond to split. Okay? And that pi bond is going to form a new bond between the radical initiator and our monomer. At the same time, the other electron in that pi is now going to sit on the most stable structure or the most stable atom. So if we were to draw this out, what we would then have would be our OR. Our initiator is still connected. And then we would have our alkene, but now as a radical. If we look at most radical reactions, what we would now do is quench that radical. And so it would be near, typically what we'd be talking about is the HBr addition. So it would be near HBr, so it could now quench and stop the reaction. Except in this case, we aren't near a sigma bond structure. What we'd be near is more alkene. So what happens, and I apologize for whatever reason my video editor or my software for drawing that structure was a little weird. That radical would now see another alkene. So it would react with that pi bond similarly. And what you might note that comes out of this is that we end up forming yet another radical. Okay, and that's what's happening here. In this process, what we end up doing is continuing out our reaction, so on and so forth, and we would encounter another alkene. The odds that we would encounter another radical initiator, another RO radical, are very, very small. Remember what we said to begin with, we want that to be very limited in concentration. We just want it to get it started. Now we just want the alkenes to react with themselves. Depending on the concentrations that we put in, we could expect this to grow to varying lengths. So we could put in more alkene or more initiator to change kind of the amount of repeating units. If we want to kind of simplify, so let's draw this out. Let's get a couple monomers into this. Get a couple monomers into this. If we were to continue this structure out, and we'll draw that in as a radical, we're having this happen hundreds, if not thousands of times. So if we were to draw out a single molecule, it would take forever. So instead, what we go through and do is a shorthand. And in that shorthand, we look for the smallest repeating unit, and we would kind of put parentheses around it. There's a couple places that you could drop in repeating units. So let's go ahead and do here and here. So if you note where I drew parentheses, okay, those parentheses represented the new bonds. So I drew it through that structure. So what I could simplify this as would now be showing the bond go through and here. And what we've got in the middle is my monomer repeating unit. If this said repeated 100 times, I could then say put in 100, or say it repeated 100 to 150 times. Okay? And we now have a shorthand. Of course, those of you that are good at looking for patterns probably notice that there's another way we could have sliced it. We could have looked at, say, this pattern. And this does become a bit of a challenge because, well, now which one is correct? And as you remember from nomenclature, when we talk about nomenclature, there's supposed to be one way. Well, it turns out there isn't one specific accepted way. There's a lot of different ways that we could cut this apart. IUPAC has tried to come in and define the standard notation for this, and that comes in as IUPAC for this one. The problem that I have with that notation is if we look back to kind of its origin, we're not slicing it in such a way, or the original polymer in such a way that we see very clearly the monomer. Because if we look, our monomer atoms are now being split across the structure. But it shows a better, higher priority system, so it reflects the nomenclature rule systems a little bit better to cut it this way. Ultimately, you can see it drawn both ways because a lot of people seem to appreciate kind of the common format. Let's call it common because we can see the monomer within it. We can see where that piece came from. If we think about how this structure built out, those are continuing bonds outwards, and those ultimately came from a pi bond. So if we acknowledge all of that system, we now know that that was our monomer, and indeed there it is. Okay, so it can kind of help us to see that process, which is kind of nice. So that's our really quick, believe it or not, summary of our polymers. What polymer are we actually looking at? Whoops, that didn't pop quite right. What we're using as our monomer, instead of just using kind of a standard alkene, which we showed in the kind of example going out to this kind of polymer, we could go through and say that this backbone is ultimately due to the alkene of our monomer, and then we had some random group kind of on the outside that wasn't really part of it. Okay, this was our random group. If we go through and look at the polymer that we're going to run, the primary polymer of or monomer of our backbone is this isobornyl acrylate. Okay, and if we look within that, there is our repeating alkene. Okay, so ultimately, all of this is an R group. Okay, and that's going to now change how those individual polymer chains connect to each other. Because remember, when we're looking at this, we're looking at a lot of these polymer chains kind of growing out from each other. This polymer has an additional feature. It has this bis-GMA molecule, and the bis-GMA is going to act as a crosslinker. And as the name suggests, the point of that crosslinker is to connect two polymer chains. So we would connect, say, in here. Okay? Depending on the concentration of the crosslinker, we may see it connect 1 every 10 polymer repeats, or maybe it connects every 1. Okay? That's going to change the overall properties of the polymer because our polymers can freely rotate because they're just chains. If we now cross-link them to each other, it limits the rotation, so it changes the polymer properties. Okay? How does a crosslinker work? Well, the crosslinker has to still connect through a polymer backbone, which is why we see out here that we have the alkene. But it has to connect to a second chain, not just a standard growth. There's the other one. So when we're going through and looking at it, this whole chunk in between is kind of an R that is the same across both. Okay? So by varying the amounts, we would change the overall properties. We could go into an experiment that played with that, but ultimately here we're just trying to have a little bit of fun and just make something pretty. Okay? To that end, why do we care about polymers? Well, where this is really tying into is a process known as photolithography, and this is commonly used in the microchip and semiconductor industries. And so what you would do is take a silicon substrate, and a silicon oxide substrate that you wanted some kind of feature behind. You would then layer what is known as a photoresist over the top. Okay? That photoresist responds to light in different features or different ways depending on what we're trying to get out of it. We would then put a photo mask. So that mask is now going to block light out except where there's holes in it. Okay, so we have this hole for, let's just call it a T-shape. Okay, so we would then expose light to the surface. Okay, in that place where we had that hole, a light reaction can occur, causing the photoresist to stay in this case. We then wash the surface, and what happens is all of that photoresist is now removed. Okay? We can then etch the surface. In the process of etching the surface, we can remove the silicon oxide. Okay? Or the silicon oxide that is not protected by the photomask or the photoresist. Okay? Once we've done all of that, we can then remove the photopolymer, and we would now be left with our final substrate with this feature connected on the top of it. Okay? So it's kind of a neat little process. We're taking advantage of light and using light to run a particular reaction for us, knowing full well that the light can't pass through certain materials. Okay? And we can use that to run reactions. That is a little bit more advanced than we really want to deal with, both in chemicals and all sorts of other fun things. So instead, what we're going to do is combine these two concepts. We're going to take a look at the dental polymer, and we're going to use it as kind of a photolithography. So what we start with in this experiment, and we'll see that in just a second, is we start with a transparency, just to kind of, I don't know how to spell transparency, a transparency to just kind of keep everything clean. We'll then put some glass cover slips on the surface of it, and those are going to act as just kind of a spacer. We will then put our polymer mixture down in between those. Okay? We can then put our substrate, so we're effectively doing this upside down, a glass slide over the top of that. Because we only have those thin cover slips, what will happen when the glass slide hits the liquid is it'll spread out theoretically evenly underneath the glass slide. We can then put on our photoresist or our photo mask. In this case, the photo mask is just a printout of an image that we wanted. We then expose it to UV light. Then we disassemble everything and clean it off. And what we should see on the glass slide would be the image left where the light was exposed. Okay, so it's kind of a neat little process. Here we're collecting the polymer mixture. The polymer mixture was made by mixing the cross-linker, the monomer, and the radical initiator. A little bit of effort because it's difficult to mix them. And then also some food coloring. So just normal food coloring. Used probably about 50-50 red and yellow because I was hoping for an orange color and that didn't really pan out the way I wanted it to. In this case, I'm using a lightning bolt because I had it as a mask, and so I know that's running on the vertical axis, so I'm trying to ensure, based off of past failures, that there's enough polymer mixture on that axis to allow us to get a solid lightning bolt with minimal air bubbles located within it too, which is why I'm kind of condensing all of the polymer mixture on that axis and adding in an extra layer on it. If you notice as well, you might see that little kind of green square looking thing. That's the glass cover slip. That has been taped down, and the green part is actually due to the previous failures. But you see there's a corresponding one on the other side, just not stained green. So here's our silicon surface. And so this is our substrate on which we're going to do everything. So we've pretty much inverted the image from the previous discussion earlier. There's our photo mask, our nice little lightning bolt. Note that we've got the dye mixture all the way around it. And then we're putting on a second glass slide, and the whole point of this slide is just to hold everything in place so it doesn't shift around and move on us. Because if it moves during the process, we're going to get a wonky looking lightning bolt. And now for the UV light. I believe in this case we're using long wave. UV light, though I honestly can't remember. And we have to leave it exposed for about 30 to 45 seconds. The point here is that UV light's going to hit the photoinitiator only where light is passing through. The photoinitiator will then start the polymerization reaction, and we'll now get that polymerization occurring where the light is exposed, because that's where that mixture is. Because our mixture is kind of viscous, we don't expect a whole lot of lateral movement, and so we should really only see the lightning bolt come out of this, regardless of how long we put the UV light on there, theoretically. Now we're done with the UV light. Now it's to clean up, which I don't show, but it's a little bit of a ethanol rinse into the waste bottle. We just kind of have to disassemble everything first. And as we disassemble it, we will see our lightning bolt. Actually, no, we won't. It doesn't make sense to see the lightning bolt yet. But now, after we've cleaned it up, there it is. Came out really nicely. We can see the exact alignment with our structure. Thanks for watching.